So homework 5 is due Friday now, and we are going to cover the another example of DNL and INL calculations. And after that, we will do our quiz on charge pump. And then on Wednesday, starting from Wednesday this week, so we'll have our lectures in the lab, in the electronics lab over there next door. Okay, so I have the TSMC 180 tutorials already ready for you guys. Let me show you this really quick. So these are the 6 regular tutorials you can see from here, cadence. And so I'm expecting you guys to finish the six tutorials, the regular cadence tutorials, in 2 weeks. Okay, it looks pretty long, but actually they should be really simple since you have already done very similar stuff in electrical VLSI. You can see the only thing challenging to you guys is the Linux environment. And so all these configurations. I can probably tell why we didn't use cadence at the very beginning. There are multiple reasons for that. The first thing is a lot of times the Linux system is a little bit buggy, and you spend like 80% of the time to configure the tools instead of learning how to do the schematic and layout. Doesn't like electrical VLSI. You probably have like 95% of the time just working on the technology or the skills, right? Instead of configure the tools. But cadence is different. You have to spend a lot of time on that. But I think after you are start getting familiar with all the environment and everything, it should be pretty simple. Especially a lot of guys already, either you are in my embedded or already took my embedded in the past. So you can do VI, right? You can do Vim. Okay, you know how to open up Vim and do all the commands. So that will make things a lot easier. It will be pretty slow for the first 2 tutorials, but whenever you move to the 4, 5, 6, it becomes a lot easier. Okay, you should be able to get everything done in a week. So you can see the last one is just to put everything in the path frame. It's not the best way to make a path frame, like the ones we are going to do after the first 2 weeks, which will be the more industry standard way to create paths for the chip. So this one is a really fundamental way to do it. Just create all these metal the top metal squares, and place the overglass on the top, and eventually place all the gates, all these components into the path frame. Okay, and wire them up. So eventually this becomes a 1.5 millimeter by 1.5 millimeter chip. It's a die. It's a silicon die. Eventually will be fabricated. You can see all these wiring and all the. You can see the thickness of the width of the wires are pretty random. So it's not a very good design actually, but just showing you how the layers work. Okay, how many layers this one has. So the thing is, because most of the PDKs, or it's called precise design kit, it's called PDK. So most of these tools or libraries are IPs of the company. So nobody can disclose them. But really interesting, NCSU is North Carolina State University. Since many years ago, probably like 15, 20 years ago, they released all these PDKs. They are probably, I don't know if you can fabricate chips using their PDKs, or they maybe just fake PDKs for educational purpose. That's why we can use it. You can still grab all the transistors from the PDK, but they all from NCSU. And it's not a super top university, but the thing is, it's the only one available on the market for everyone to use. Even people in MIT and Harvard are using NCSU PDKs because it's free and open source. You don't have to sign NDA, so a lot of people are using it. However, the one in the PDK, the most common one is AMI 06, which is also 600 nanometer technology, similar to C5. So that's why we're using C5, because everyone uses C5. That's the most common one available, actually, for everyone. However, after going through all these tutorials, let's see what's the plan here. We go to this one. Okay, see, this week on Thursday, it's lab 9, okay? So lab 9 is cadence tutorial 1 to 3. And next week, Thursday, is cadence tutorial 4 to 7. But you can see there's only 6 tutorials, and the 7th one, I cannot post it because it's a TSMC's secret, right? So TSMC's their IP. So for you guys already signed the NDA, I will post it to the Dropbox and send you the link. So make sure you don't disclose it to anyone, even within the department. Just keep it within this class, okay? You cannot disclose it. And you can, if you search online, even though it's already like a 15-year-old technology, maybe 20, I don't know. I think back in 2005, the TSMC 180 was the most popular one, because everybody was saying, hey, you are using TSMC 180. That's considered as the most advanced node available. That was 20 years ago, but still, it's still top secret. If you search online, trying to find out the parameters of the PDK, you won't be able to find it. Everyone, okay? So today will be the probably maybe one of the last lectures covering the theory, and then we'll do a quiz on charge pumps. So the charge pumps is gonna about the circuits and details of things like this. Oh no, this is sample hole. Could be this one, right? So why you are having this one in its own well, right? So what are the voltages oscillating at these nodes? Why is it bigger? Why is it smaller? Okay, and why is it smaller? Why is it bigger? Things like that. For the quiz on Wednesday, so we talk about the timing of the star ADC over here. So like I said, it's not the only solution for the timing. It's probably even not the best solution by far. I'm trying to, I found some more examples online and trying to duplicate it into LT Spice. But before I figure that out, let's just use whatever I have for now. Okay, we don't have other options. So this one, study this, watch the lecture, record a video, and prepare for the quiz on Wednesday. Right. So for the ones came a little bit late today, just let you guys know, since from Wednesday this week, we are going to have the lectures in the lab, okay, to work on the hands-on tutorials. All right. So one thing here, it's about there's a homework assignment in homework 5, which is due Friday this week, about the DNL and INLs. Okay, so why we are doing this, because once we got our ADC simulated for the course project, I'm going to ask you guys to plot the DNL and INLs. There must be a lot of ways to do that, but eventually we just have to just pick up one of the methods to find it out. Okay, so it could be a time domain plot. All right. So for example, if you have a curve like this, okay, like this, even though it doesn't work well for the lower voltages, but for example, for this part of this curve, right? You just do the subtractions to find out the INL, DNLs and plot it in the time domain, which is totally fine. If you look at the papers published in IEEE solid state circuits, this is one of the top journals. You can see. So whenever you guys are looking at journal articles, you can see this one, for example, this one, right? How do I identify a good journal or a bad journal? If you have experience, you should be able to tell. Even though you are searching for impact factor for this journal article, IEEE Journal of Solid State Circuits, right? If you search for the impact factor, it's probably only like 304. It's 304, right? If you search for the biomedical or nano-related journal articles, the impact factor can go up to like 15 to 20. Okay, but doesn't mean that this is not a top journal. This is the best journal in circuit design, actually. Okay, I mean, if you are a integrated circuit professional is probably, are getting like 5 or so at most for a whole lifetime. It's really considered the best. And there's a conference for the same society. It's called IEEE Conference of Solid State Circuits. It's ISSCC. And I remember back in like 15 years ago, for the whole Chinese area, the China, including China, Macau, and Hong Kong, and Taiwan probably. No, not Taiwan. Taiwan has more. But for China, Macau, and Hong Kong, 15 years ago, for the whole area are getting maybe up to 3 conference papers published or accepted by the conference every year. Is that crazy? So it's the top conference and top journal in this area. So so this one is published in there, and if you look at the INL and DNL plotting, how do they plot it? It's in the time domain. Okay, so it's okay to plot in the time domain and look at the maximum DNLs or INLs, and make sure that none of them are more than 1 LSB. Because if it's more than 1 LSB, you are getting a incorrect code in your final converted result. So just find out the journal article and see how they plotted the parameters for the ADC, and we'll just do the same thing. Very simple. All right. So the course project, I was not sure that if we can put everything, manually lay out everything in Cadence. But after spring break, I think I'm pretty confident that we can, because I was testing all the DRC and LVS tools over there, and it all worked. So we will, I'm gonna let you guys duplicate everything here in Cadence as a course project. So eventually you guys will be a master in Cadence. It's called mixed signal design, right? So it's including both analog and digital, right? I'm thinking if we should do 8 bits or 4 bits. Maybe 4 bits instead of 8 bits. 8 bits is too many circuits in there. Let's start from 4 bits probably. Pretty poor resolution, but start from taking baby steps instead of getting you guys stressed out. Okay, so that's the plan. Okay, while we are calculating DNL and INLs, so we are going to use it for the course project. So we were able to cover the calculation for the DNLs for the DAC, not ADC, but the DAC. How do we do that? See here, it's a 3-bit DAC, and these are the digital inputs. So 3 bits is giving you A combinations of the inputs, and this is the actual voltage output. Okay, so not all of them are ideal, equal to the ideal values. So these are the ideal output. This column, the 3rd column. And firstly, I plotted all the axes because the DAC is the digital input, analog output. So digital input are pretty confirmed, nothing to change. So from 000 to 111, just plot it. And then I labeled all the ideal outputs over here. And then I drew all the stairs, and the straight line is ideal straight line. Just across all the ideal values. So however, the actual output are not all ideal. If you compare, you can see 0 volts, 0 volts, 0.625, 0.625, and the next one should be 1.25, but actually I'm getting 1.5625, okay? So which is labeled over here. So in that case, if you draw it in the diagram over here, and you can see the DNL, I can probably make a note. So DNL is comparing the step size. Keep in mind, DNL is comparing the step size. So every step should be 1 LSB. It's a actual step size minus the ideal step size. That's the DNL. So DNLs are just comparison about the step size. Okay? So you can see this one, what's the step size over here? It's a 1.5625, which is the value here, and it jumped from 0.625. So from here to here defines the step size. Okay? And so that's why I was looking at the digital input, which is 2. Okay, so it has to be DNL2 equals 1.5625 minus 0.625, and that's the step size. It's a step size, and that step size divided by 0.625, which is 1 LXB. So 0.625 is 1 LSB. The step size divided by 1 LSB equals how many LSBs for that step, right? Ideally, it should be just one LSB, should be just one step, or 1 LSB. However, since it's not 1 LSB, since I can tell the difference, that is why you are using this one divided by 1 LSB, so you are getting how many LSBs for that step. All right, and then minus 1 LSB, because I told you DNL is comparing the step size. The ideal step size is 1 LSB, and the actual step size is this much LSB. Make sense? Okay, so this is the real LSB, this is the ideal LSB, it's just always 1 LSB. So it's always something minus 1 LSB equals something. Okay, so this is the first DNL you have. The first DNL you have. For DNL3, let's see. Here is 2 volts, and ideal value is 1.875, but it actually jumps to 2 volts from 1.5625, right? So the step size over here is 2 minus 1.5625, which is from here to here. That's a step size. All right, and you want to divide it by 1 LSB and minus 1 LSB to get that DNL at this point. So it's 2 minus 1.5625 minus 1 divided by 0.625 and minus 1 LSB, which is negative 0.3 LSB. All right. So just keep calculating for the rest of the points, so you can get DNL 4, 6, and 7. For INL for this one, INL is comparing the absolute value to the ideal value on the line. So let's look at the first example. For example, INL2 here, INL2. So INL2 will be, let me put on the paper probably. So DNL compare what? Comparing the size, right? Step size. INL. Absolute value, probably amplitude. Let's do amplitude. This is differential. Nonlinearity. It's integral. Yeah, Ian was working on the wire bonder during the break, and he worked on that already a few days before the break, and eventually we figured out something, and he got some successful bonds yesterday. So during one of the labs, I'll let you guys bond some of the pads on the chip. Okay, it's gonna be a really cool experience. It's almost ready for you guys. What about NL? So DNL we already have DNL2 to DNL7, and now let's look at NL. NL is actually comparing the amplitude of this guy to the amplitude of the point on the ideal curve. Right? So what about the first NL? NL2, right? 1.5625. This point, right? This point. So it's the amplitude minus the ideal point on the curve, on the ideal curve. So minus 1.25, sorry, 1.25. So that's the difference. And divided by 0.625. Do we need to minus 1 LSB or not? Nope. So this is 0.5 LSB. Right? Another point, we have an NL here. Definitely this point, right? You can see the actual value is not on the curve. So it's going to be NL3 will be 2 volts minus the ideal value, which is 1.875. .2 LSB. So this one we might have another one here, but I think I missed it. Let's skip this one for now. NL6. So 6 is the actual value is 3.4375, this guy, and the ideal value is 3.75, right? So it becomes 3.4375 minus 3.75 divided by 0.625, which is negative 0.5 LSB. Now let's come back and look at this one. So because it's comparing the amplitude, so of course whenever you see a voltage which is not equal to the ideal value, there should be an NL, right? So there should be an NL for NL3, and we already did it. So what about this one? 4. Oh, 4 is 2.5 and 2.5, so there's no NL for 4. Okay, for all of them, it's fine. So there are only 3 points have a nonlinearity here, or have an NL here. Okay, so it's 2, 3, and 6. It's pretty simple. It's just looking at the actual values, right? So these values are the amplitudes. It's just comparing these. If there's a difference, then there's an NL over there. Okay. For ADC, it's very similar. ADC. Have an example here. ADC's input output. So these are all the analog inputs and digital output, and I do analog input for the transition, and it's followed by a curve. So I'll draw this really quick. Two, three, four, three. I'm skipping one. No. So ideally it should be this. It's ADC, so it's analog input and digital output. Skipping one. So ideally, the transition looks like this, right? Yeah, there's nothing else over here, I think. So these are the points, the numbers. And now let's look at the input and output over here from the table and find out the DNLs first. Let's find out the DNLs first. So let's label it to the curve. This is the ideal curve, but it's not what's actually happening. It happens at these nodes, right? So these nodes are, for example, this one here. This is still correct. 0 is 0, no problem. 0.625 is 1 OSB. It's getting 1 OSB, no problem. And 1.25 is giving you 2 OSBs, but actually it waits until 1.5625 to jump to number 2 instead of 1.25. So basically, it's not jumping at this point; it's jumping at this point. Okay, so on the curve, it looks like this. It's actually extended to here and then jump. So it generates a DNL here. And then we look at this code. So it's a DNL2. DNL2. So what is DNL2? Keep in mind, DNLs are comparing the step size, right? DNLs comparing the step size. Where's the step you are looking at? Start the step in your analog input, right? So you can see from here to here, it is 1.5625. So DNL2 is, because this is number 2, okay? That's why it's a DNL2. DNL2 has a step size, real step size, from 1.5625 minus 0.625. Divided by 0.625 and minus 1 LSB. So that is 0.5 LSB. Do you have a second DNL here? Do you have another DNL? So keep going. Keep going. Another transition happens at 2 volts. So it's actually here, right? So it goes through here. 2 volts. And then jump. Okay, so you got a DNL3. It's from 2 minus 1.5625 divided by 0.625 minus 1 LSB. That equals negative 0.3 LSB. And the next transition happens at 2.5. So even though this one got delayed, but it's still transition at 2.5. Okay, so even though it happens at 2.5, but the thing is the last one got delayed. So the thing is the step got smaller, right? So you still want to count that one into it. So it becomes 2.5 minus 2 volts, which is 2 over here. So it's going to be a DNL4 is 2.5 minus 2 divided by 0.625 minus 1 LSB. That equals negative 0.5 LSB. And then it keeps going. 0.125, no problem. 0.125, no problem. So it happens at 0.125, then jump. Then 3.4375 instead of 3.75. So it happens here. Okay, and it jumps to here. So that's a DNL 6. And that is 3.4375 minus 3.125. Divided by 0.625 minus 1 LSB, and that is negative 0.5 LSB. And eventually, it's both this, but the thing is the last one got delayed, so there will be another DNL. Okay, even though they both happened at here. Transition happens here, no problem. But the thing, the step size is different from the ideal one. So DNL 7, which is this step size, which is 4.375 minus 3.4375 divided by 0.625 and minus 1 LSB equals 0.5 LSB. That's how I calculate the DNLs. So for the INLs, so DNLs compare the step size, INL compares amplitude, right? So INL, you look at the analog value here and minus the analog value here on the ideal curve. Keep in mind, the INLs are comparing to the points right on the ideal curve. So what do we have here? So first, NL2. It's this one minus 1.25. This one minus 1.25. So it's 1.5625 minus 1.25 divided by 0.625, which is 0.5 LSB. I have another one, NL3, here, minus here. Two minus 1.875 divided by 0.625 equals 0.2 LSB. And these are all right on the curve until this point. There's a little difference here. So that is NL6, which is 3.75. Wait. Oh, you use the actual one minus the ideal one. 3.5 4375 minus 0.75, 0.625 equals all right. That's everything about the INL, DNLs for ADCs and DACs. Very boring, right? But in the real world, you are able to use the tools, for example, Cadence, to